Good evening to all of you, those who are, attending from this part of this globe, and good morning to the rest of the people. We are at the third week of this webinar series, that is Saturday Manufacturing Talks. In this webinar series, we have, the eminent academician and industry professionals discussing on various topics of manufacturing. So they are giving us their thoughts, their vision, which will help our Center of Excellence in Advanced Manufacturing Technology to grow. And I believe their vision and their thoughts will also create insight in the minds of the academician and the industry professionals of different institutes and different places and all. I'd like to, give you a very brief introduction about the Center of Excellence in Advanced Manufacturing Technology. It's a very new center that started 3 years back. So this introduction would be made in the form of a small video of 7 to 8 minutes time, followed by the today's speaker, Tapan Bagchi, and he will deliver his lecture about 40 to 45 minutes time. And after that, we'll have the interactive sessions. So this is the pattern of the flow that we are maintaining for this webinar series. So now we'll play a small video about the Center of Excellence in Advanced Manufacturing Technology.
There is no sound. Is there? Should there be sound?
Tata Steel, HEC Ranchi, and BHEL. Researchers at Center of Excellence in Advanced Manufacturing Technology are working in 4 thematic areas such as specialty materials, design and automation, additive manufacturing, and Industry 4.0. Research projects are getting carried out in this newly developed Center of Excellence, which is a 40,000 square feet, the area. We are giving training to the MSME sectors on advanced manufacturing concepts such as computerized numerical control. We are also planning to give training on the most wanted topic, which is the industrial robotics. This Center of Excellence is open to all industry sectors, starting from the big to the very small, and also to the startup. So the startups can come forward, they can use our facility to nurture their concept and build up the early prototypes for their, the product.
The developed system employs cloud infrastructure for managing the sensory data, deriving real-time insights about the welding process, and subsequently controls the FSW machine by sending optimized parameters. This has been achieved by employing various signal processing and machine learning techniques. So this has been a very cost-saving solution as it eliminates the material rejection and there is no need for performing the quality test as well. I am quite excited that the developed solution is now filed as a patent with Tata Consultancy Services.
In a very short span, the Center of Excellence in Advanced Manufacturing Technology has developed a very low-cost artificial intelligence-based Industry 4.0 solution for real-time dimension check of the product. This solution will immensely help the MSME sector.
This innovation is about a low-cost Industry 4.0 solution developed for the MSMEs. It is a customized software embedded with computer vision, AI, and ML algorithm that takes pictures of a product and measures the dimensional features in real time. It also checks the surface quality as well. Here, we used for the image capturing a very low-cost webcam as the software intelligently enhances the image quality in real time, which eliminates the cost of an expensive camera.
We have tested a variety industrial products such as those used in transmission lines, automobiles and mechanical tools. We have obtained accuracy close to 99% within just 10 seconds.
We are also lucky to have Tata Sons as our industry partner. What we basically want to do in this particular project with the help of IoTs and also the traditional manufacturing systems and the logistics systems and with the application of digital technologies, we are trying to improve upon the efficiencies so that the products become more competitive, the steps are also optimized, and moreover, a very good optimization can be built with the large enterprises along with the SME sector.
One of the major gain points for any industry is to tackle the unplanned breakdown. So in collaboration with Tata Metallics, we have developed this software where we have leveraged Internet of Things, IoT and machine learning algorithms to come up with a predictive maintenance software. We have created this dashboard for annealing furnace which is fitted with a gearbox where we can tell in what mode the machine is running and when it is about to fail. This helps Tata Metallics a lot. They have estimated that in indirect cost they can save up to 1 crore rupees due to the increase in productivity. In the direct cost, they can reduce the downtime by 40 hours, man hours by around 400 hours, and 8 lakhs in the wastage cost. If such software is available for our MSMEs, which is very simple to implement and very cheap, that can help them drastically, and that is actually the real meaning of Atmanirbhar Bharat.
This center is one of its kind in the whole country, we can say, because the facilities and the infrastructure which has been created, it's really unique, and it will be of great help to all the MSMEs for quality manufacturing of products which otherwise they cannot do. Some of the work which we have done in last couple of years is of very interest to be noted here. That with the help of TCS, we have developed a real-time monitoring and control of defects on any manufacturer, which is one of its kind, because a lot of products are wasted. If online, on the go, if the welding is going on and we can find out the defect and control, I think there is nothing like that. And hence, the software has been developed in consultation with TCS. The second thing which has been done is low cost, real time, you can say, dimensional control. The other third product we have done is through a software which talks of the predictive maintenance, and this is a unique one which has been which is being used in Tata Metallics, one of the companies. And with these three things we are progressing, but then we have bigger plans to come up with some of the trainings which are already going on some of the budding apprentices which are available with BTech degree or even diploma degree. We are trying to train them for working in different heavy industries or in advanced industries, or also can become entrepreneurs, as well as this facility will help the MSMEs. And through this, we will also like to enhance our capability for robotics and virtual and augmented reality in near future as well. So with this, I think we are progressing, and we are planning to have all sorts of even bigger industries to come and get the quality product made. And this will go a long way in serving the all companies, including the MSMEs. Thank you.
It is my real pleasure to introduce Professor Tapan Bagchi. Professor Tapan Bagchi holds a BTech degree from IIT Kharagpur, MSc and PhD from University of Toronto, and BSc from IIT Kharagpur. A registered professional engineer, Ontario and FIE India. He served as different capacities at different institutes, such as Professor, Dean, Director at IIM Lucknow, KIIT Bhubaneswar, NMIMS Sirpur, MDS Infosat Mumbai, NITI Mumbai, SP Jain Dubai, SPG IMR Mumbai, IIT Kanpur, IIT Bombay, and IIT Kharagpur. Till 1987, he served Exxon Mobil Corporation in Canada, USA, Europe, Singapore. He received Exxon's Extraordinary Contributions Award. He has authored 7 text books and published over 100 journal papers in different fields such as computer science, operations management, quality engineering, scheduling, Bagchi methods, value at risk, and genetic algorithms. His YouTube lecture series on Six Sigma have been viewed over 3 lakhs views. Currently, he lives in Lake Town, Kolkata. With this small introduction, I now request Professor Bagchi to deliver his talk today on design of experiments in engineering and science. Professor Bagchi. Sharing access. Sir, you are on mute. Professor Bagchi, you are on mute. Professor Bagchi, you are on mute.
Okay, now, am I audible now?
Yes, you are audible now. Yeah.
I'm audible now.
Yes, sir, you are audible.
My respected professor, Professor G.S. Khan from IIT Kharagpur, he's there. And my old buddy, Professor Farooq Mistry is there. These are the people I can see. Pravanjan is there. And I just saw, 1 second. I saw here, Paul Milton. Is Paul there? Paul must be there somewhere. Those of you who have a control, please turn your video on so I can actually see the faces also. Many of you already have your faces on. Is Paul there? Paul is right there, yes, waving his hand. My God, look at that handsome man there. He's a very young, he's in his 20s, by the way, I should tell you. I shouldn't disclose people's ages. And there's Siddharth right there, and Shekhar Nath is there, and Professor Anup Kanti there, and a whole bunch of people. I think they are probably, some they are just going to sleep, so I couldn't really. Shrupatik is there, Shrupatik Bhattacharya is right there, Asim is there. And I think it's going to be a wonderful time, the next 30 or 40 minutes that I want to spend with you, and hopefully show you a few new tricks with some of the methods which are basically statistical, but they are awfully useful for us. And let me just see if I could turn my slides on. I have to do sharing and to do that using the PowerPoint. So just bear with me for a minute. It will all be there. We should be there momentarily. Now we are getting there. We are just getting there. Okay, slide number 1. Now, never mind whatever the slide is, these are not numbered, but each of these is pretty important. The very first one is the one that you have on the screen. Now, someone please just speak up and say that yes, you can see the slide. Anyone, just say yes. Or wave your hand so I can see.
Yes, sir, we can see the slide. It's fine.
Okay, you can see the slide. Good, good, good. That's just great. That's the starting point here. I have a couple of things that I've done with this slide. I have obviously given you the title, and I've given a couple of references which you may copy later on, or we'll try to make sure that you get these links and you can look them up when you're on the internet. You can do that. Now, notice this slide has a whole bunch of rocks that are put together. And these rocks actually have very little cement between them. Most of these are just laid on top of each other. This configuration is from Nepal. This wall is approximately 500 years old. And the way to develop this wall was totally empirical. There was no theory available, no structural engineering available, except what was done later on. They put a slab there to give support to some of the parts there. But otherwise, this wall that you see there is actually developed empirically based on experiments. What do I mean by that? It turns out, if you look at systems around us, you see kind of a spectrum of various types of systems which we have around us. On the left-hand side, we have weather, then we have economy, then we have psychology, and so on and so forth. And on the right extreme, I have a digital watch. I could obviously put a cell phone there. There's a big difference between the kind of systems we have on the left-hand side and the kind of systems we have on the right-hand side. The ones on the left-hand side, we know very little about. We really do not know how these systems function. It's just not known to us. Our knowledge has not progressed to the point when we can predict weather exactly, or the state of the economy exactly, or human behavior exactly. We just cannot do that yet. On the right-hand side, of course, we have the product of a lot of PhDs, and these PhD research work, actually, they have produced theoretical equations. There are a lot of theoretical models that have led to the design and functioning and proper functioning of systems to the right. So on the left, we have zero theory available. On the right, we've got 100% theory available. I'll give you some examples of this later on. In between, in this range here, we have all kinds of real systems that are around us. For example, we've got medicine, we've got chemistry, we've got engineering, we've got many other systems which I've not listed here. But I just thought I should add COVID into this. COVID is probably, the talk of the town right now. We know a few things about it, but still a whole lot of things we are not really aware of. For example, the vaccine that is being developed for COVID, it's all being done empirically. Now you notice there's a egg-like shape there. There's an oval shape there. That oval shape roughly encloses all those systems that can be studied and optimized using experiments. And the technique that is used for this is design of experiments. You cannot do design of experiments on the left-hand side because you do not know what factors are controlling weather or economy. So I cannot really conduct experiments on this side. On the right-hand side, I need not really do an experiment because I already have the theory for it. I'll give you an example in a minute. In between our systems, where we can list the factors that might be affecting the response of these systems. But we do not exactly know how exactly that happens. For that, we really need this technique of design of experiments to try to do this. Let's move on here. Here's a theoretical model. This is a model that's based on theoretical work done. This is not based on experiments. This is really based on fundamental understanding of science and some engineering. And that's how this has been put together. Of course, the example I show there is coming from financial management. It's coming from accounting, and those principles have been utilized to construct this equation. What is important for us to realize is when you've got complete knowledge about the system, when you've got complete theoretical knowledge about the system, generally one is able to write the response as the function, as the mathematical function of the input variables. That's what we have here. So we have the exact equation that describes the behavior of the system. That's like the kind of thing that I have with the electronic device, for example. We know exactly the Ohm's laws and Kirchhoff's laws and so on. Those have gone into building the equation that has gone behind designing the system here. But that is quite different from the state of the art here because we do not have the theory there. And in the middle here is a place where we can apply some experimental work to try to generate something that can kind of work as pseudo-theoretical model. And that's what we do. Now, what exactly is an experiment? Here's the situation. In fact, just days ago, I was in a bunch of experts and farmers, various factors. For example, they were changing the moisture, they were changing fertilizer, they were changing soil, they were changing a variety of things to try to sort of see somehow if they could raise the output of the farm. That was their goal there. This work does not have an equation available for us. This task does not have a theoretical equation available for us. So what we have to actually do here is conduct experiments in a very systematic way. We've got to conduct certain trials and measure the output, identify the response as a function of the input variable there. Now this actually, we owe this technique to the gentleman whose name is Sir Fisher. He was a statistician who worked about almost like 80, 90 years ago. He was in UK and he was actually asked to come and help with increasing farm output. That is just around World War II, when farm production in Europe, and particularly in UK, came down very drastically. And he found ways by which certain special experiments could be done and you could raise the output of farms without doing anything extra. Let's move on. But again, we do not have the theoretical model available. This is the case is such, the Nissan company, they sell their cars and the cars are pretty darn good cars. These are good, reliable Japanese cars. But the problem here was many people came back and they pointed out that the logo that was stuck on the back of the car, it just kept falling off. So many times they lost their logo altogether. They had to be back at the dealership to try to get another logo. Why was this happening? That was not known and no equation was available to describe the strength of the amount of force you require to peel off these logo from the thing. No theoretical model was available. But what was available from the people who worked in this area, who worked in this process was the different factors that actually were being utilized to try to set this logo at the back of the car. These were the different factors there. I'm going to bring this up. I'm just going to bring this up in a couple of minutes here. Now, one other thing I should point out is you do not really list, when you do brainstorming, when you try to collect the different factors that you have to study experimentally, you do not actually list them out just like this. You start with what we call a cause and effect diagram. And some of you might recognize this is the same as the fishbone diagram. That fishbone diagram is the starting point for conducting experiments. What is it that we are trying to do in design of experiment? We're trying to establish causality. That means we are trying to find out which factors impact the response and to what degree. If we have that knowledge, then of course we can control the system and we can optimize the performance. That's what we can do. All right, how do we go there? You look at any real system, you'll find a whole bunch of variables involved. There are so many variables. Some these you are controlling, these are control variables. Some, of course, are given like raw material, for example, and labor and so on and so forth. And then there are a whole bunch of other factors that you have no control on: vibration, humidity, ambient temperature, and so on. These also might be impacting the process. The result is, when you look at the output of the process, it has a wide variation. That's not something customers would like to see. Now, again, how do you improve a process like this? What do you do to try to improve a process like this? The recourse is design of experiments. We'll take a look at a couple of new examples. The starting point, again, is the Ishikawa or the fishbone diagram. I have an example here. I have a table lamp. Let me just bring up the lamp to show you exactly that I'm not talking nonsense. Here's the lamp. You can basically only see the lamp. And that sometimes that lamp does not come on. For some reason, the lamp does not come on. What could go wrong? Why is the lamp not turning on? One could do brainstorming. But look at the power factor. The power could be one of the reasons the lamp is not turning on. The bulb may be defective, the lamp may not be right, the plug cord may be defective, frayed, and so on. Any of these two could actually cause this lamp not to go on. Trying to find which of these factors might be causing this, we may have to conduct some experiments. So we'll probably pull the plug out and see if that turns it off or on. And we change the lamp, we do that. We actually switch power or we turn it on and off and so on. So a variety of different things we could do with these factors to try to see, could we fix this problem there? If we take an engineering example, here's something that some of you might be familiar with. This is a welding process which is not behaving right. You saw in Dr. Paul's presentation that they are working to try to get the IoT techniques applied in a way so that the welding process with a certain types of joints, metal joints, would work better. But actually, they are playing with different factors. And they are actually, they are working with people who are very familiar with the welding process itself. And those people, they contribute domain knowledge. With the help of this, with the help of that, you can actually construct this cause and effect diagram. So on the right-hand side, you got the responses that you want out of the weld produced. So that will be like the mechanical properties of the weld joints that you produce. And there are various factors. The tools that you're using, the fixtures you're using, the material you're using, or the machine you're using, the welding machine, the action force, and so on. Now, these all are variables. But the point to remember is, for a system like this, we do not yet have a theoretical equation that will give you the answer just by looking at the values of these variables. We do not have that equation, the kind of equation that I showed you earlier. That we do not have. So what we have to do is we have to conduct experiments to try to sort of see, can we discover the factor effects? Can we find some of their interactions and so on? Now, sometimes if you're just standing around, you can observe a lot of things. Here's an example. People smoke, and people smoke packs of cigarettes. Some people smoke. Some of them they smoke, do not smoke at all. Some smoke half a pack of cigarettes. Some use probably just one pull, and some smoke 1.5 packs per day. Some smoke 2 packs per day. And on the right, on the vertical axis, I have the severity of cancer. Some of these people might, end up with. And so actually, it is not really unknown right now. But what you're really trying to do is you're trying to sort of see, is there an association between the packs of cigarettes smoked per day and the severity of cancer produced? Now, on this diagram, you see a rising trend. That means the more I smoke, the more likely it is that I'll have cancer, or probably severe cancer. Now, notice here, of course, there is a rising trend. That is like something that might suggest there's an association between these two factors. One factor is this is the input factor, this is the response factor. But of course, you see many scatters also, a whole bunch of scatters. That is because there are other factors which are also probably affecting the formation of cancer. And that's why this experiment is not complete. We may have to incorporate in this more factors to try to make sure that I get the right answer to cure cancer. That would be actually when I had to go back to a cause and effect diagram like this and see which of these other factors might be causing cancer, then conduct an experiment by incorporating these factors also in doing our experiment. If I see correlation, this correlation actually suggests that there is causation. Something is causing something just because there is correlation. For example, when temperature goes up, we start drinking more Coca-Cola. Or when temperature goes down, we start drinking more coffee. Is one causing the other? We actually see an association, but this is not correlation. For that, you've got to conduct experiments again to try to make sure that you've discovered the causality. So correlation is not something on which you can count on engineering solutions, produce good engineering solutions. You cannot do that using correlation. Here's the guts of the talk tonight. The talk tonight really focuses around this slide here, and I'm going to walk through this somewhat slowly. On the left-hand side, there is actually some question in the mind of the user who's interested in the performance of some system. That system actually has a few factors that might be affecting it. So notice on the left-hand side, speculating causality. There is some response, and I'm speculating the factors that might be leading to that response being down or up. And I've got three factors here: factor A, factor B, and factor C. When I conduct the experiments, I'll be changing the settings of these factors and have to observe the output. And to do that, I have to really progress pretty systematically. So let me give you an example. This is not going to be a very complicated process. All I have to do is I have to select factors, and here I've chosen to use factors only, three factors, factor A, B, and C. And I really use here settings. I use a particular scheme by which I'll be combining these different settings of these factors together. For example, factor A is here. It could be set at a low value or at a high value. That's the working range for factor A. Similarly, for factor B, I've got two settings possible. I have a low setting possible for B, and a high setting possible for B. Same thing goes for C. Now, the total process here will involve some setting for A, some setting for B, and some setting for C. And it could be one of these 8 combinations. The task of DOE is to try to discover which of these situations. These are actually 8 prototype experiments that I could do. 8 prototype versions of the process that I can create by varying the level of A and the level of B and the level of C. And because I've got 2 levels here, 2 levels here, 2 levels here, the total combination possible is 2 times 2 times 2. That is, you see these 8 different combinations which are there. When I conduct my design experiment, I must conduct each of these 8 trials. Then I do data analysis. I collect the data from there. I do data analysis. And the object of doing data analysis is to discover the effect of these factors. For example, someone may ask, is the effect of A important as far as the process is concerned? Or is the effect of B important for the process? Or the effect of C important? And which of these 3 factors has the strongest effect and which has probably the weakest effect on the process? This I can do by analyzing the data that has come out of the experiment. That analysis actually is going to give me something that I call main effect, which are like factor effects. Then 2 or 3 of these factors, their effects may interact with each other. And also, their effect may be significant when you look at the effect of factors which have been left out of the experiment. That's the noise factor. Now, suppose I only look at the main effect. That is what is shown in the plots here. The plots here basically are showing when I change the setting of A from low to high, the response seems to go up. That's probably good news for somebody and for the process. When I change the setting of B from low to high, response seems to come down. When I do the same thing with C, it seems to come down again. And it seems to be coming down faster than it did for B. Now, the data analysis is so tricky and so good that actually this data analysis is going to separate the effect of A, B, and C for me. Just by doing the proper kind of analysis. By doing the proper analysis, if I conduct these 8 experiments here and do my analysis properly, I can separate out the effect of A and B and C. That's exactly what I'm after. There may be interactions also possible, and we'll see that later on, how we actually take care of that. Now, suppose I've done that. The same data can be used by me to construct an equation. This is something like a regression equation. But this has got the factor settings A, B, and C sitting here, and also the interaction term AB there. This equation here is almost like the theoretical equation that I showed you earlier. So what we've done here is we've conducted some experiments, we've collected some data, and we've done some calculations, and based on that, we can go ahead and construct this regression model. That's a big, powerful output out of this effort here. So the output here is not only going to be knowledge, but also some versions of the process, some model of the process, which I can then utilize to optimize the process, which could be reduced variation in the output or reduce defects in the products produced in each of these things. So that's like the overall view of this. This is what I'll be preserving as I move through my slides. I'll be continually referring to this slide there, and sometimes we'll be working with the causal effect diagram. Sometimes we'll talk about the designs. Sometimes we'll talk about data analysis. Sometimes we'll talk about plots and the regression model. All this is going to happen tonight itself. So just hold your breath. We're going to get there. Now, there's a technique that has become quite common in industry now. That's called the Six Sigma technique. What it really does is, it's an approach by which you can reduce defects in a process. If you have a process that is producing defective products. For example, I have some examples here. I have a bad product in my hand. I'm just going to bring out, this is the bad product. And suppose I have to redesign this product then, and I really have to work very, very hard to be able to do that. Six Sigma is something, Six Sigma is a technique that actually helps you do that. One of the key parts of Six Sigma is design of expert. It's got many other techniques also involved in it, but one of the key techniques that you utilize when you are doing process engineering using Six Sigma is to use design of expert. So that's like, it is the most powerful technique utilized within the Six Sigma framework. And again, we've already seen what DOE is, design of experiments. An experiment is actually a test of a series of tests, and we'll see that. And all the experiments, they are actually designed, they are not random experiments. That's something we got to remember. Here's the theoretical model, but just because for many systems, we cannot construct the theoretical model yet, we got to go back and do some experimental work. And that can lead to mathematical models also. It can lead to regression models. So my experimental work will not only tell me which factors are important, which are not, it can lead to actual mathematical models that I can then utilize to optimize the system there. Here's an example for which there is no theoretical answer. Chocolates are, of course, dear to everyone. I don't think there is anyone in the audience who does not like chocolate. If you just tell me, then I'll substitute this chocolate by something else, maybe a strawberry jam or something like that, or a nice piece of cake. In any case, chocolates actually are also notorious for poor performance. If you're in a tropical country, like I'm conducting this lecture from the city of Calcutta. Calcutta right now has become pretty warm, and temperatures have risen up to 40 Celsius. And the best chocolate that you can find in a store, the moment you take it out of a fridge, it will begin to melt. And that actually, if you look at ambient temperature on the x-axis, look at the plasticity of the chocolate bar, you'll find that a chocolate that is not designed well, that has not been engineered to perform well, it'll start melting when temperature gets high. But a chocolate that's well designed, well formulated, the recipe has been adjusted, it'll give you a robust performance. And again, to go from a system like this to a system like this, so you can succeed in the marketplace, is again to conduct experiments. That's like another application of designed experiment. Or if you're playing golf, you may use different types of drivers. That's the hockey-like stick that we use. See this guy there? He's standing there with the driver there. And he's got his ball on the ground. And he might be riding a vehicle to go from a hole to another hole. And he might be drinking some beverage. Each of these things might be affecting the score. Each of these factors might be affecting the score. How do we discover the proper combination of the driver and the ball and the riding and so on? So that again, we can conduct design experiments. And we can use different types of balls, we can use different types of drivers, but we must use a scheme, must use a design, must use a scheme. And that scheme is called the factorial scheme of playing with it. And with that, you can combine, you can simultaneously study 2 or 3 or 4 or 5 factors together. That can save you a lot of time. And these are just other schemes which are used if you're trying to optimize your golf game. And you see 2 situations here. Here's a factor. Are you going to be using a cart to go from hole to hole when you're playing golf? Or are you going to walk? These 2 alternatives, they may actually affect the score. To find that for sure, to establish that for sure, to conduct experiments. There will be no argument. The experimental data will tell you exactly what you have to do. Now, here's a situation when an experiment was done, but the environment was very noisy. The result was this, the real effect of this, if there are 3 factors involved, 3 settings of the factor involved. The big first what is problem is. Some drugs, for example, cocaine can actually impact your heart rate. Sugar will hardly have any impact on your heart rate. And if you don't take any drug at all, of course, that will not really change your heart rate. But let's say somebody comes and he starts arguing that cocaine has no effect at all on your heart rate. You can conduct experiments. If the experiment is designed well, you'll see factor effects like this. You see this to be a small height, and this to be somewhat of a medium height, but this will turn out to be a very large height. That actually tells you that your heart rate really goes up when you have cocaine. Now, suppose this experiment was not done properly, not designed properly, your output would look like this. You see the wide range of data for the no drug situation. You see the wide range of data when there is only sugar being taken and the wide range of data there. If your data comes out like this, there is no way of telling whether there is any impact of taking cocaine or sugar or no drug. You cannot say that if your output actually looks like this. So what you got to do is you got to make sure to avoid noisy experiments, or indeed if you have noisy experiments going on, you apply another powerful statistical technique called analysis of variance. If you do ANOVA on this data, it can come back and tell you with a pretty high reliability that yes, cocaine actually has a pretty bad effect on heart. Here's the case study now that I'm going to describe. You want to catch your breath. Are you tired of listening to me? Or just listen to this story for a minute. This is the Nissan logo that was stuck on the back of the vehicle. And the vehicle actually stood by there. Many people bought the car because the car was good. But when they started to use it, after a while, the logos kept falling off. It was bad news because they wanted, obviously, they wanted to show off that they have a nice Nissan car in their hands. Now, suppose it was like this. How do you fix this problem? How do you hold the logos from falling off? Well, the easiest thing to do is go and talk to people who are using this process to stick this logo on the back of the car. So they will give you these factors. They will tell you, well, sir, these are the factors that we try to adjust by our guesswork. For our experience, we try to set the area, the kind of glue we are using to stick that logo there, or the thickness of the foam that is being used. Some styrene is used to try to make sure it gives the glue a chance to stick on the wall. The thickness of the logo itself, the logo is a metallic logo, so that's the thickness of it that might have some effect of it. The amount of pressure that you apply when you're applying the logo on the back of the vehicle there, and the pressure application time, you hold it for a minute or 5 minutes or what. And any primer that you might apply on the paint, that also may have some effect there. Now, the easiest thing to do is to try to find out which of these factors really has a big impact. We'll see that in just a couple of minutes. We'll see how I can discover which of these factors has a large effect. This I'm going to be doing by conducting experiments. The first thing I have to do is, of course, the experiments, I will not be holding these steady. I'll be changing their settings. The settings that are available to me are the low setting and the high setting for each of these factors. So actually, I've got 2 settings per factor, the first factor, 2 for this, 2 for this, and so on. So actually, there are 2 to the power 7 combinations possible of these settings there. But just to save time, what we did was we selected only 4 factors. We said, let's conduct the experiments using only the top 4 factors. Then we had to use a plan. And that plan is a lot like what we have here. This is the kind of plan that we'd like to have to set up basically the different experiments. For that, we will actually need a plan like this. I'm going to show you the plan now for the factors that we have there. Notice here, I have a matrix. I have a matrix here. And those of you who are close to the screen, perhaps you can see that the different factors here, the addition area, the type of glue used, thickness of foam, and so on, those have been tagged here as A, B, C, and D. Each of these factors has 2 possible settings, and I've coded them as plus or minus. Plus or minus for each of these factors. In effect, what I've got is, I've got exactly what I have here. I have these 2 settings here, I've marked them as plus and minus. And then I'm going to combine them. How I combine them is dictated basically now by this blue box. The first experiment that I'll be conducting will be setting A at plus level, B at plus level, C at plus level, and D at minus level. I'm going to tell you later why we set exactly like this and why not some other combination. The second experiment will be done as plus, plus, minus, minus. Now, when the first experiment was run, I looked at the response. And the response here was the force with which I was peeling off that logo on the back of the car after the curing was done. And that required 9.8 pounds in this case. And this is the sum of 2 tests. So actually, 1 test just gave you half of this amount here. So it would be actually half of this, 4.9 would be the value that you'd be having for 1 run of this experiment. I do the same thing with the second experiment. The settings have been changed. I get a value of 8.9. The third one, which is a plus, minus, plus, plus, those settings would lead to this strength, this amount of strength, the double of the strength there, 9.2, and so on and so forth. After I complete all these experimental trials, I do my data analysis. These are the experimental data. So this is what I'm sitting here with when I look at this diagram. This big fat arrow there, that arrow is actually this column. That arrow is this column here. I do my data analysis, and I produce now, I can actually tell you exactly how to do this, but just assume it for a minute that I've told you how to do this, and I found the factor effect of A, the average factor effect A to be at the plus setting, 4.6 pounds. At the lower setting, minus, I've got 6.4 pounds. For B, I've got 5.5 and 5.5 again. C, I've got 5.65 and 5.42. These are the average strength required for me to peel off the thing when I change the setting of A from plus to minus. Now, let's go back to this, into this, just a bit, one more time. Notice, look at the setting of A. Setting of A is set at high. High is the plus sign when A is small. And setting of A is tagged as low, which is a minus sign, when addition area is 20. So when area is going from plus to minus, I'm actually increasing the area. I'm actually increasing the area. So here the setting of A is going up from plus to minus, and in effect what I'm doing in the actual trials is I'm increasing the size of the area, the addition area of the logo. That's what I'm doing there. Now if you go back to the effect calculation, the larger area, which is this adjustment here, requires to apply a larger force. So it agrees with intuition. If I have a smaller area, which is this just sitting here, I actually have to apply less force. So actually, the larger is the area, the more force I have to apply. But are they all equally kind of forceful? Are they all equally effective? I can do that by doing a simple plot. Let me do that plot for you. The plot turns out to be like this. Look at the effect of A. This is the factor A, and it has got two settings there, plus, which is the lower area, 15 square centimeters, and minus, which is the larger area, which is 20 square centimeters. And notice here, gluing strength actually has gone up. So if I increase the size of the logo, if I make it a bigger logo, I'll have to apply a larger force to peel off the logo. That's like something that will be very useful for the designer, the guy who's going to be designing this mounting scheme. But look at the effect of glue. Hardly there is any effect if I change the glue. And also there is very little effect of this and very little effect of this. Some effect is there. Of course, if I want to, I can actually construct my real process by using the best setting for A, best for B, best for C, and best for D. So to design the process to release it commercially, I should set my A at this minus level, which is the larger area, glue at this setting there, thickness at this setting, and thickness of styrene at this setting, thickness of the logo at this setting there. So if I combine this, and this, I should really get the maximum strength for the logo to stay on the back of the car. If I look at the back of the car, and if I use those settings there, that logo should really get me a better performance than what my customers are experiencing. That is like something that has come out now as a result of the experiment. Of course, there is something I have not done here yet, which is like perhaps these different factors, perhaps their effects interact also. This is a bit of a complication for which you only need a little more refined experimental scheme. If you do that, then you can discover the effect of interaction. Sometimes this is important when you're trying to optimize something. It is important for us to make sure that we understand interaction and we utilize that when we are trying to optimize a process which has got interaction present in this. This is especially true when I've got 2 or 3 different factors there and their effects are not additive. This is a very important concept. If the factor effects are additive, I can optimize them independent of each other experimentally. But if their effects interact with each other, I cannot apply the additive principle to try to optimize the process. This is like something that's very, very important. And this is done particularly when you're trying to do something called response surface. Now, let's get into this a little bit more and see how people conduct experiments. You know, these guys are our old friends who flew their airplanes 100 years ago, or maybe more than 100 years. Those were the Wright brothers. They were actually bicycle mechanics. They did not have theory with them. They did not go to an aeronautics school. They didn't do that. But they could build prototypes. They built their prototypes and they conducted experiments with them. And that was actually the starting point of conducting experiments and looking at the effect. Now, these are not the only people who are conducting experiments. If you look at Elon Musk, you've seen his rockets go up and come back. Sometimes the rockets come back all right, but they explode. Because Elon Musk does not have the theoretical equations to launch his rocket or design. He just does not have that yet. But the kind of rockets that he wants to go up in the sky, go into space, and then come back again and land safely, she does not have the theoretical work done for this. That might require maybe 10 PhDs at Stanford or someplace like that. That has not happened yet. So what he has to do is he has to conduct experiments, and his approach is do trial and error. So please don't panic and don't curse him if you find Musk's rocket blowing up, even in future, for example. Because the only tool he has no theory with him. He's got to conduct experiments to be able to do that. So experimentation is actually a pretty big help for us to try to move from left to right on that big spectrum that we have there. Now, suppose somebody says, I'm not going to mix up the variables A, B, C, and D. I'm not going to mix them up. I'm just going to conduct one factor at a time experiment. I have a sister. My sister is a PhD from Europe. She's a chemistry professor. The unfortunate part is that she is a big fan of one factor trial. And let me show you the kind of experiment she runs. I've taken the data from her. Now, here's something for which she's looking at a chemical process, and she's got two experimental variables, temperature and pressure. So when she talks to me, she calls me Dada, and she says, Dada, what should I do? I've got two variables, and I really have to find the effect. I've got to find the best way to raise my yield. The only method I know is to change temperature and observe yield at various points. And here's a plot I have. And then what I do is I change my experiment, and I again measure my yield by changing pressure. She's got two experimental variables, temperature and pressure, but she runs two separate one factor at a time experiments. Do you see the problem there? The best value here does not coincide with the best value there because their effects interact. In fact, the real process has this sort of shape, where you've got again pressure and temperature, but the optimum cannot be found by finding the best value for pressure only, or the best value for temperature only, and hope that you hit the best spot. That just does not happen because this is a complicated process. This is not an additive process. You got to remember that. The additive process would probably allow you to do this if this was additive. But because it's not an additive process, I have to go to superior methods. I've got to actually utilize better techniques for conducting the experiments and also better ways to analyze the data. And I'm going to give you some examples. Here's another very crazy process. It's still got only two variables, two input variables, because the two input variables there. And let's call this the x-axis and the y-axis. And on z-axis, I've got the response. And look at the crazy behavior of this. Do you ever feel that by conducting one factor at a time experiment, by changing this one, or only by changing this one, I'll find the best value there? It's just not possible. Because nature is complicated, and nature always puts up challenges like this. So we've got to have better method for doing this, and we'll get a glimpse of this. How do we study a process like that? Suppose the real process had a response like this. And I had a feeling that there is interaction between these two factors there, factor A and factor B. So what do I do there? I have to conduct a special type of experiment, something that's going to catch the interaction. This is quite different from the experiment that we did before. It's also not a one factor at a time type of experiment. Because what we're really trying to do is we have to sample space. This is the response surface. We got to sample it various ways. And one way to do that is to use this special design. And look at the special design, how it spreads around. I got to actually sample the process at each of these. Only then I hope to produce something as a result of my analysis that will look like the real process. This is what led to the technique called the response surface method. This is a very powerful method. And with this, you can study some very complicated processes. But obviously, it requires some knowledge of statistics and some knowledge of optimization. So now you're going a little beyond standing in the farm and throwing seeds around or your fertilizer around or sprinkling water. You got to do a little more work. You got to actually come up with a plan like this. If you get a plan like that, you can eventually construct an equation like this. And this equation can then substitute for the theoretical equation that would be for all of us the dream to have. Because this equation can let me optimize the process and we can reach the peak without doing anything else. Once I got this done, How did I construct this? I collected my experiment data, I did some analysis, and I applied the regression methodology, and I was able to generate this equation here. Now, when would you do experiments? You really should not try to do experiments when you're doing production. That's pretty bad news. It's too late to discover knowledge as to what causes what. You should do that when you're doing R&D. When you're doing R&D, it is right then and there we should conduct a lot of experiments. That is not the time when you're producing products or samples of products to sell in the marketplace. That's not what you're doing in R&D. That is the time when you're generating knowledge. But once you're through with that, and with your design optimized and you've got validated thing on, then you go into your regular production. Then of course you'll have fine quality and fine production and good output. All those things are possible if you've done good work with R&D. Now let me tell you, because I spent a good bit of my life in industry. I was a R&D engineer in ExxonMobil for over almost like 2 decades. And can you believe this? I worked with chemists, I worked with chemical engineers, and many of them had very poor understanding of statistics. They never heard of DOE, and they could not actually work with multi-factor systems. Most of the chemical systems and metallurgical systems and even mechanical systems, these actually are a multi-factor situation. You cannot do them you cannot optimize these systems by doing one factor at a time. I mean, with all due respect to our mechanical engineering friends and so on, unless you are doing DOE, you will not really discover the real guts of the process. That is just not possible. Let's see some examples. The system is there, and it's got some factors, and we got to make sure we incorporate these in our experiment. I've got to use a scheme, and those schemes are available. Very quickly, those schemes are available. And those will obviously cost you some money. So what you got to do is go to a professor who is probably a professor in statistics or industrial engineering, someone like that. Someone like our Professor Paul Milgram, for example. He can guide you with this. And so do many other people. Make sure they understand your system, they understand your objectives, and all the stuff that you've got in your hand that you want to play with, that you want to do the experiments with. And then you come up with the scheme, and the scheme itself is going to be looking like a matrix. I'm just going to give you a glimpse of that. I'm not going to spend a lot of time. Here I've got 3 factors. This is the 3-factor factorial experiment. I must apply in my experiments, I must apply the settings different. I must combine the different settings for each of these factors, but done in a very special way. Notice here I've got low, low, low. Those are the 3 settings for the first experiment as far as these factors are concerned. Then I've got low, low, high. And for each of these trials, of course, I do repeats. I do I measure the responses, and I do that. I would do that for this, I do that for this, and so on and so on. Where do I get this from? You get them from books on statistics. If your books on statistics, they will tell you exactly what you have to do to try to make sure that you conduct the experiment properly. Suppose I've done that, I will be getting these, outputs here, which are like these. Then comes the part of data analysis, and data analysis will tell you which factors are important and which factors are perhaps not important. If you got a system with many different factors, it may take you a long time. In fact, it may turn out that the first round of experiments you have to throw away. You have to throw away the results because you'll discover effects there that perhaps nobody is suspected. I had a professor, my dear professor, Professor Jim Templeton. He taught me this technique. And I asked him, sir, tell me, many times I do not find results that I like. What do I do? And you know what he told me? He said, the best time to run your experiment after the experiment. The best time to run my experiment is after the experiment. So yes, in the first round or the second round, you're only learning about the process. You're trying to understand what kind of scheme I should use, what kind of data analysis method I should use, and what kind of modeling I should do. For that, you actually have to conduct perhaps 2, 3, 4 rounds of experiments. You'll end up with something that will be like absolute cream puff. I think I've given you enough. It's night time, so you'll probably, I just want you to, say to yourself, I heard something called DO, design of experiment. And it's got a whole bunch of things there. And there's something called measurement. When the output comes out, I got to make some measurements there. And please make sure you're measuring instruments. Those are calibrated properly. You know exactly what you have to do. You can differentiate between accuracy and precision. Like these shots, they are not precise. This guy is actually precise but not accurate. And these three arrows there, they're on the target and also they're close by, so they're accurate as well as they're precise. This is the kind of system that you require if you really want to have successful experiments done. You must have a calibration system where your responses are measured, and please make sure that before you conduct the experiment, it is done like this. I have a very dear student who is now the vice president of the Wipro company, the Wipro IT company in Bangalore. His name is Jugal Prasad. Jugal worked with me. And Jugal was actually doing practical experiments in a place where they produced plastic parts. And Jugal had all his cause and effect diagram done and everything. He had taken to heart this scheme. He knew exactly what he had to do and so on. But when it came to designing, when it came to doing the data analysis, I'll show you exactly what his results turned out to be. His results turned out to be like, just coming up in a minute, not like the airplane there, something close to that. His results turned out to be like this. And he came back and he told me, Professor, what you teach is all garbage. Because look what I got. I plotted my data and the data looks like this. Now, what do you suspect was the problem? Can you guess what the problem was? Anyone? Can you speak up, please? Can you hear me? Can you hear my sound? Just venture out and just say, perhaps this is the reason why data would look like this. This was Jugal's experimental data that looked like this. Why did they look like this? Can you guess? Anyone? Devashish, can you hear me? Hello, Devashish. Are you there?
We can.
Why do you think the data look like this? They came back from the experiment. What was wrong?
Data was noisy.
Sorry? Of course it's noisy. Yes, yes. Where do you think the noise came from? Can you guess?
From various sources.
Okay, good. That's a very good idea. And there could be something pretty obvious. Can you guess? A big source of noise was, let me give you a hint. A very big source of noise was, let's take you there. A very big source of noise was, guess what? It was this. The measurement instruments. The measurement instruments he was using were bad. This noise, the real effect was totally lost. Is this clear? Is this clear, folks? You got to make sure you do your cause and effect diagram really, really well, and you talk to people, and you train your technicians, and do all those things. You've done everything that is possible. But the problem is, my God, maybe the measurement instruments themselves are bad. And many times what happens in companies, they do not calibrate their instruments. These are being used by production people, by technicians, a whole bunch of people there, and they do not take good care of their instruments. So when you apply any of these instruments to make measurement, for example, dimension or something, they may give you all kinds of data. And those data may not be the effect of, may not be caused by the factors which are there, but they're probably caused by the instrument itself. And that is actually not very helpful in doing scientific work. So please make sure your instruments are accurate, your instruments have good precision, and if you study this area a little bit, you'll be able to tell between the difference between sensitivity and specificity. These are like concepts and measurements and metrics. And our professor here, we have two professors here, Professor Kant and also we got Professor Faruqi. They are experts in this area. You talk to them about measurement, they can talk all night and they can really, really build you up as far as the background is concerned. These things. This is kind of, you might say this should be the starting point before you go into. Professor Paul, are you still there, Surya? Are you there, sir?
Yes, sir. Yes, sir.
Okay, so let's see. Can we open it up for some questions?
Yes, I think because we are running a bit short of time, so
Yeah. Maybe just a few questions if people would like to ask questions.
it was a really, it was a wonderful, the lecture describing the design of experiments from its fundamentals and giving a very nice example of the task sticker. So, identifying various factors. So I'd like to, place it to keep it open for for any questions from anybody from the students from here, the Omkar.
Anyone, if
then,
you have a question, I'll be happy to answer. Of course, I've got my guru sitting here, so they will answer for me. If I fail, I'm pretty sure they'll help me out. But if you have any questions, please go ahead and fire up. Actually, we've covered a lot.
Chat box.
Yep. Go ahead.
So one question has come from the chat box, like how to manage measurement of wear and tear. What is that? Devasis, can you read that question?
How to manage wear and tear.
Repeat the question, please.
How to manage wear and tear.
How to manage
Measurement and tear.
measurement and
Measurement and tear.
I think it is related to the calibration of the instrument, I believe.
Oh, okay. To give you a very quick answer, I can give you a very complicated answer, but let me give a very quick answer. There's a technique called gauge R and R. Gauge R and R. Gauge reproducibility and repeatability study. If you do that with an experiment, and there are many books in this area, and usually books have a chapter on this. And those will talk about basically the behavior of instruments, and those can actually tell you what to do if your instruments are not behaving right. And this is something that actually cannot be escaped. So the question is this: how do I make sure my measurements are good? Is that your question?
Is there one more question?
No, hold on. Was that your question? That how do I make good measurements? How do I get good data? Was that your question? Okay, if that is a question, and if you're using instruments, just take a look at this, this concept called gauge, R and R. Write it down. Gauge is B-A-G-E, gauge, and R, the letter R and R. This is the technique that applies specifically when you've got instruments. And you have to make sure the quality of the instrument is good. Yeah, what is the next question? Second question?
Another, how this DOA technique and this Six Sigma applications in the industries, in manufacturing sector, basically in any.
Okay, you should not try.
In any product.
Okay, good question. Very good question. We face problems, our industry face problems when production is going on.
Yes, sir.
Many times you find industries facing problems when production is going on. The unfortunate part is when production is going on, you are worried about trying to get production out the door. You do not have time to study the process and optimize the process. Our gurus will tell you this repeatedly. So it's not time to stop production and conduct your experiments when actual production is going on. It's too late for that. But many times you really need to do some hit and trial. So at most you can probably use experienced people. You can ask them which way should I adjust the flow of the pump or temperature or something based on experience only. But the right time to conduct the experiments is when you are doing R&D. When the product is being developed or the process being developed, it is still in the lab. If it has gone out of the lab and if you've not done design of experiments in the lab itself, you're in for big trouble. So please do not attempt to do DOE at the production stage. That's too late for you to try to adjust the process because it will be by hit and trial. It will be like building an airplane and making it fly. You saw that airplane crashing? You see our Elon Musk rocket crashing? Just say yes or no. Have you seen his rockets crash?
No, sir.
Tell me, have you seen his rockets come down and crash?
Oh, rockets. Yes, yes.
Yeah. Elon Musk is the guy who is trying to reach Mars. His mission is to go and settle on Mars. But he's building these reusable rockets. And his rockets take off and they go into space, they launch maybe a satellite, then they come back. And they're supposed to land basically at the same spot from which they were launched. But many times when they come back, the control is not good enough, so they crash. So Elon Musk is in a production mode. He's in production mode. He's trying to do R&D. He's trying to do R&D when he's actually doing production. His production is to launch the rocket. Is this clear?
Yes, sir.
Gentlemen, is this clear? What Elon Musk is trying to do? First of all, do you know the name Elon Musk? Yes or no? Who asked the question? Somebody asked the question.
Yes, sir. Myself, Omkar.
Sorry?
Omkar.
Okay. The response is this. If you're trying to conduct experiments during production, it's usually too late. It may be quite expensive, like it is for Elon Musk. He's trying to do experiments at full scale. These rockets are not 5-inch rockets. Those rockets are 100-meter tall rockets. And many times those rockets blow up. When they come back, they do not land properly and it just crashes. So actually you can conduct experiments in production, but it can be very expensive for the company. Instead, if you do this when you're doing your R&D, it's not very expensive and you can actually control many of the factors. The only factor that will be different between this and full production is the actual scale. Actual scale of the product will be different, and that scale itself can be a factor that might be affecting the quality of your process. And I experienced that when I was in ExxonMobil. I experienced that in the test tube our process worked fine, but when we scaled it up to a reactor, that was like the size of this room there, and it just did not behave the same way. Because Reynolds number changed. Reynolds number is a concept that's in fluid mechanics. Reynolds numbers are quite different when you look at a tube versus when you look at a full-scale reactor. So there, if you're conducting experiments in the test tube itself to hope that I'll scale this up and I'll build a 200 feet tall tower, that will be a big mistake. You should not do that.
So one person from the one of the persons, Mr. T. Ramaswamy. So he has asked the question how to evaluate the multiple. How to evaluate
closer to the mic. Speak closer to your mic. Go close to the mic.
Yeah, the question is how to evaluate the sensitivity of multiple effects of the factors affecting a process. This is the question asked by Mr. T. Ramaswamy.
Oh, okay. I did not get into the calculation, but entirely possible, and possible because the scheme of the matrix. You see, the matrix is designed very, very cleverly. The matrix, when you do your data analysis using that matrix, when the data comes out, it actually spits out the effect of the individual factors. So even if the matrix looks complicated, it's very rich matrix in terms of its content. The contents are so rich that you can separate out the effect of each of the factors. Perhaps we could do another round of, another session on the calculation of the effects themselves. And it's very possible to do a multi-factor trial, then come back at the same time and come back and separate out the effect of the main factors. And that's really what I was showing when I was showing you one of the results there. I was trying to show you that I can calculate the effect of A and the effect of B and the effect of C. In fact, I worked this out with one of your friends there, Devashish. Devashish and I, we did some calculations and separated out the effect of A, B, and C. More questions, please? So what you do is, I will give you my email. Send me email. Contact Professor Surya Pal, and he's going to relay that question to me, and I'll be only too happy to help you to give you the answer for that.
So we have typed the email ID of Professor Bagchi. It's tapan.bagchi@gmail.com. So if anyone having specific questions, then can be to Professor Bagchi, or it can be sent to me, and then I forward, consolidate all the questions and then forward it to Professor Bagchi. My email ID is surjo.pal@icloud.com and surja.pan@icloud.com. So any questions, if you have got any further questions, you are most welcome. You just place those questions, send those questions to me, and then I'll consolidate and forward it to Professor Bagchi.
Sir, Nilanjan, I'm very happy to see you. I see Nilanjan's face there. Hello, how are you? This is really wonderful to have you. So please contact even later. Thank you so much, Professor. Professor Kent is here. I'm just thrilled to find my way. Thank you so much, sir. You have been very patient to sit with me all this.
Sir, it was the wonderful experience. I think the audience have enjoyed your wonderful lecture. We are really grateful to you for your time. And with this, we finish today's the lecture. And then next week, that will be talk on AI-based sensing for advanced manufacturing. The date is 3rd April, next Saturday, 8:30 p.m. again. The same time, it will be delivered by Dr. Orpon of Tata Consultancy Services. So with this, I'd like to conclude today's, this event. Thank you so much.
Thank you, everybody. Thank you. Thanks, everyone.